this is an optional demonstration regarding some of the other data analysis methods. I would like to introduce correlation coefficient analysis because some of your data might be all continuous or all categorical, and you won't be able to do the interaction using t-test or ANOVA test. So here is a situation when in our horizon data you have height and weight, and your question is you're interested in whether height and weight has a statistical significant correlation. If there is, how much of weight can be explained by height, or how much of height can be explained by the weight. So in this kind of situation, you want to use a correlation coefficient to analyze two the continuous variables or two categorical variables. So let's state the null hypothesis for the height and weight situation. We can say there is a significant relationship between height and weight. So in this case, we are only looking for the correlation between the two, and we did not indicate which one is a dependent variable, which one is an independent variable. We're just saying these two variables, these two continuous variables, are correlated with one another. And in the SPSS Grunk's book, in chapter 5, there are also specific explanations of what are the situations when you can use correlation coefficient. So if I go to the horizon data set in Citrix or in Virtual Lab, I can go to Analyze, and I can go to Correlate by Variate, and I wanted to get to height. There is a significant relationship between height and weight, so I put height and weight in it. And if these both of the correlation variables are continuous or ratio or interval variables, I will use Pearson correlation coefficient. So you just click on Pearson, and this is by default is Pearson. But if it is one is categorical, one is continuous, you can use Kendall's tau. And if both are ranking order variables like grade, level, and free lunch status, if you have the ranking order kind of ordinal data, then you need to use Spearman correlation coefficient. So in this case, I'm using height and weight, which are both continuous variables. I'm using Pearson, and I'll click on OK. So here is the data interpretation for correlation coefficient. So the mean of student height is 67 inches. The mean of student weight is 170 pounds. And the Pearson correlation coefficient between student height and student height is 1, because basically you are saying these two the same thing. But student height and student weight in pounds, this relationship is 0.480, and with two stars here, it indicates if its probability of error with a two-tail, because we're just saying there is a relationship. We did not say which one is greater. So in this case, it's a two-tailed probability test, and the p is less than 0.0000, which means the probability of error, type 1 error, is almost 0. It's 0.999. 0.000 less than 0.0009. So this 0.840 is the correlation coefficient between weight and height. And if you sometimes it's symboled as R of weight and height equals 0.480. And on the other side, the student weight relationship between student weight and student height is 0.8480. So it depends on whether you use height and weight or weight and height. The correlation coefficient R equals 0.480, and this is called correlation coefficient. if you square this, that means the overlapping between height and weight, or how much of weight can be used to explain height. So that's sometimes called R square. So if we square 0.48, it would be something like 0.23. And that means 23% of someone's weight can be used to explain height, or can be used to predict height. If that is the case, this R square is called coefficient of determination, which means the overlapping of weight and height, that something they share in common, is 23%. Or in another word, 23% of how much a person weighs can be explained by their weight. So how much of a person is going to be, let's say 71 inches tall, and that 23% of that can be explained by someone's weight. So that's called coefficient of determination. If you wanted to look at further, you can use a bar chart, a scattered plot. So if I go to scattered plot, and I use a simple scattered plot here, and I can say define x-axis is height, y-axis is weight, and usually if we specify this way, that indicates student height is a dependent variable and student weight is an independent variable. In another word, we're using weight as a significant predictor of explaining how much people can how tall you are. So we can say your weight is a predictor of your height. If you are using scattered plot, you have to think about which one is using as a dependent variable and which one is using as an independent variable. The reason I'm doing this because I'm thinking about weight and height. Usually it's I'm thinking maybe we can use weight to predict how tall you are. And also on the other side, we might be able to think that we can use height to predict how heavy you are, because in a sense, the higher you are, the more weight you have to be in some way. So I can say, okay. And you will have a scatter plot like this, and if you double click on that, and there is a fit line here, or you can go to element, and you can say that you wanted to show the fit line at total, so you can click on that, and you have a line of fit there, and with the equation. So that's the R square, which means the common area that both height and weight share is 23.23, which means 23% of your weight can be used to explain your height, because height is a dependent variable here and weight is an independent variable, the way I did it. But you can obviously you can do the other way. You can say weight is a dependent variable and height is independent variable, and look, and it will be the same thing. It's a 0.23 because these two are something they share in common. And that concludes correlation coefficient with two continuous variables. If you want to do a correlation coefficient with one continuous, one categorical, you can use Kendall's tau. So for example, I can say I'm interested in height and student grade level. So in this case, height is a continuous variable, grade level is a categorical variable. So I can use this and one categorical and one continuous variable to look at the correlation coefficient. I can use Kendall's tau, and I can say okay. And here again, the correlation coefficient between student height and student grade level is 0.341. That's correlation coefficient R, and the R square, you can do a graph, or you can do a correlation coefficient graph here, and look at the R square, and you go to scatter plot, a simple scattered plot. So in this case, you are doing student weight and explained by grade level. So grade level is an independent variable and weight is a dependent variable. And I can say okay. And you can do a line fit here. Again, go to element, line fit, and you can say okay. And in this case, r squared is much flatter, is 0.016. And if you have two categorical ranking order variables, and you can use Spearman-Brown correlation coefficient. For example, you are interested in there is a significant correlation between free lunch, which is a ranking order, and we can say parents' education, which is also categorical ranking order, because we have free lunch with no free lunch. We have free lunch is definitely lower in socioeconomic status, and no free lunch is at basically some higher in terms of socioeconomic status. And parents' education is also a ranking order with no education, somewhat education, and also professionals and doctoral education. So that's also a ranking order categorical variable. If that's the case, we can use Spearman-Brown, and you do the same thing. You say, okay, Spearman-Brown, okay. And in that case, you can see the correlation between free lunch status and parents' education is 0.133, and the P, the probability of error, is larger than 0.01 or 0.05, which is the error, type 1 error is 0.189, way much larger than it should be, what we said as a benchmark. So in this case, we can say truly there is no significant correlation between parents' education level and the children's free lunch status. Thank you.